Hey, folks, welcome to Science Talk. I'm your host, Jim Massa. I want to discuss with you an article that was just published in Nature of August 2022. And the article is The Arctic has warmed nearly 4 times faster than the globe since 1979. And published in Nature, and the sub publication is Communications, Earth, and Environment. And the lead author is Mika Rantanen, and see the other researchers involved. Pretty much looks like most of them are Finns. I'll read you the abstract. And Mika actually posted a thread on Twitter highlighting the findings. So we'll be bouncing back and forth between that feed there because in his Twitter post, he posted a lot of the key figures from this paper. So to me, it just makes sense to jump right over to that, pull up each of the figures, and discuss. So, from the abstract, in recent decades, the warming in the Arctic has been much faster than in the rest of the world, a phenomenon known as Arctic amplification. Numerous studies report that the Arctic is warming either twice, more than twice, or even 3 times as fast as the globe on average. Here we show by using several observational data sets which cover the Arctic region that during the last 43 years, the Arctic has been warming nearly 4 times faster than the globe. Right? 4 times faster than the globe, right there, which is a higher ratio than generally reported in literature. We compared the observed Arctic amplification ratio with the ratio simulated by state of the art climate models and found that the observed fourfold warming ratio over 79 to 2021 is an extremely rare occasion in the climate model simulations. In other words, statistically significant. The observed and simulated amplification ratios are more consistent with each other if calculated over a longer period. However, the comparison is obscured by observational uncertainties before 1979. Our results indicate that the recent fourfold warming ratio is either an extremely unlikely event or the climate models systematically tend to underestimate the amplification. Well, we've never heard that before, have we? Well, as we'll see here, they use a lot of the CMIP models for their analytical work. CMIP is Coupled Model Intercomparison Project, which is something the IPCC uses. And we know the IPCC never underestimates. I hope you realize I'm being really snarky and sarcastic, which is why I still say the PIK folks out of Potsdam, Germany, they use they don't use the RCP CMIP model. They use their own models that they developed, which is strictly data input, and of course with the equation and so forth. And it's called Climber, and that to me is just it's a little more accurate. It's not a little more. It's a more accurate modeling system that they're using. Faster warming rate, and this now into the intro. The faster warming rate in the Arctic compared to the globe as a whole is nowadays considered a robust fact. The phenomenon called Arctic or polar amplification AA, can be seen in both instrumental observations and climate models, as well as in paleoclimate proxy records. Okay, we're talking isotopic fractionation, right? Where we can reconstruct past climates using the ratios of oxygen, carbon, nitrogen, so forth, and even looking at pollen grains, the radiolarians, the diatom, etc. During the last decade, multiple factors have been proposed to explain the potential causes of Arctic amplification: enhanced oceanic heating, that's a big one; ice albedo feedback due diminishing sea ice, that's a big one. In fact, typically, this factor, the loss of sea ice, is what many think is what really is enhancing uh, Arctic amplification because, well, warmer oceans melt the ice from below, prevents the ice from forming. But as you have more open water, you can then absorb more sun energy. So the oceanic heat, well, water heat from below, the sun energy from above, we're losing the sea ice, and that really warms things up because you're losing the albedo, less reflectance back to space. Okay, and they mentioned a few other like Planck feedback, lapse rate feedback, its surface inversions, etc. Ocean heat transport, meridional atmospheric moisture transport are important factors as well. Furthermore, the reduced air pollution in Europe may have contributed to the Arctic warming during the last decades because of the aerosol masking effect being removed. And they mention here possible reductions of Asian aerosols under a strong mitigation policy. Basically, the aerosols that are present when you burn fossil fuel actually keep the warming a little cooler than it would be without the aerosol. Well, we're trying to burn cleaner stuff, trying to switch to renewables or green energy. So the aerosols are being reduced, and now we're removing the aerosol masking effect. So we're actually helping to warm the place. And they go on to say there's little consensus on the magnitude of the recent Arctic amplification. And they go on to say that, twice, three times. And they go on to say that their study says four times. Now, this is an important point here. The warming can be calculated using linear trends. Well, don't use linear trends. Please just take the data, find the function that best fits it. Likely it's not going to be linear. It's going to be polynomial or exponential. Okay. And the area of Arctic can be defined using the area poleward of 60 degrees north, 65 degrees north, or 70 degrees north latitude, or using definitions not based on latitude. And this creates a whole bunch of headaches because you want to be consistent. And if different papers start using different latitudes as their baseline, well, you know, the comparisons are not going to be valid. Now, the great majority of papers have looked at 60 degrees north. They argue in their methodology, they chose the Arctic Circle. Arctic Circle is approximately 66.5 degrees north latitude. The issue I have with using the Arctic Circle is that the Arctic Circle is not a fixed latitude. It changes. It changes depending on the tilt of the Earth. As the Earth tilt increases, and usually wobbles between 23 and 26 degrees. So as it goes closer to 26 degrees, the latitude of the Arctic Circle actually moves south because there's going to be further latitudes that can be included in receiving 24 hours of sunshine. The definition of the Arctic Circle is the latitude where the sun does not set at all on summer solstice and does not rise at all on winter solstice. That's the minimum latitude where that takes place. As the planet tilts up towards 23 degrees tilt, then the Arctic Circle latitude actually moves north because not so much of the planet is basically aimed at the sun. So that's constantly changing. So that's really kind of a quibble I have here. Well, let's put it this way. If I was a referee looking at this paper, I would basically say, do not state the Arctic Circle for the reasons I just mentioned, but pick a latitude. You want to pick 65? Fine. Pick 65. They use 66.5. Fine. Pick 66.5 and just state it. And then all your subsequent research that continues on from this, you use 66.5. That is at least a fixed latitude. The Arctic Circle latitude changes. And if it changes, that's going to, in my view, make any comparisons suspect at best, invalid at worst. Kind of my argument with the IPCC constantly moving the baseline. First 1750, then 1850, 1880s, 1920. No, it makes the comparisons basically worth shit. Okay, yeah, I stated my objection there, but in their paper, in their defense, they did stick with 66.5. But if in the future, if they find that the and the Arctic Circle latitude will change, so now you're going to have to like redo your analysis to either include data, remove data. It becomes a major pain in the ass. So just state, we're going to use 66.5, give you valid reasons, justify it, and then in all your future studies, you use that 66.5 and be consistent. And then they go on to say the first objective of the study is to quantify the magnitude of the AA by looking at a whole bunch of data, et cetera, et cetera. And then they get into the results here and observed Arctic amplification. So now we start getting into some of the figures here. And I think that'll be a good place to take a pop over here. And basically, they're nice enough to, open access paper. That means it ain't behind a paywall. And I will include the URL. I've been, what we're looking at over here, what we're just looking at was the URL. I will include that in the comments section. So, thread of the main results. Okay, I like this. So let's take a pop. So what they're showing here is, let's see if we can just there we go. That's what we want. Temperature anomaly in degrees C. And they list the different observations here. So you can see it starts from basically before 1960, 1950 or so, up to 2020. And see this line right there? See where it's kind of fade-ish? That's the global temperature increase. Okay. This is the Arctic increase. So what they're basically getting at, and I'll show this later at the end, what they're basically getting at is that this slope is 4 times this slope. That's how they're saying that the Arctic is warming 4 times faster. The slope of the line through the data point is 4 times the slope of the line through the data point for the rest of the planet. So from 66.5 to 90 latitude, this is your slope. From everywhere else, probably from the equator to up to 66.5, that's your slope. That's what this basically, that's their findings. So that's what they're talking about with the fourfold Antarctic ratio. That's this ratio from this to that. one reason for the higher ratios is we define the Arctic properly with the Arctic Circle. Well, I've expressed my concerns with that and calculated trends since '79 when satellite data really became in use. And then they had, based on these different data sets, the Arctic amplification, and then they give the 5%, 95%. These are the confidence intervals, or actually like two, plus or minus two standard deviations. They say the Arctic is defined as the area north of 66.5 north latitude. Okay, if you want to fix the latitude as that, fine. But if you're going to stay, it's with the Arctic Circle, and the Arctic Circle is changing. You got to be careful. Next figure. More importantly, the unabated warming in the Arctic over the last 2 decades has raised the moving 43-year Arctic amplification ratio from 2 to 4. Early estimates of 2 to 3 times warming may thus be outdated. Regionally, the warming has been even stronger. Areas in the Barents Sea near Novaya Zemlya have warmed up 7 times the global average. And we see that here, right? There's Novaya Zemlya right there. Here's the Barents Sea. You can see that a lot of the heat, this dashed line represents the Arctic Circle. So we can see the warming trend. This is per decade. And so question is, why is we see such a warming right in this region? Well, there's a thing called the Fram Strait. And we've got that warm North Atlantic intermediate water, which arises from the Mediterranean Sea. And that is just hauling ass right into the Arctic, and this gives off its heat right in its vicinity. While the Barents Sea, which is right about here, is pretty much ice-free now, year-round. You got all this heat coming in right in. I've done numerous prior videos discussing all of this. We got, it's just, it comes in and moves on the Eurasian side before looping around to the North American side. But it's bringing in all this heat, atlantifying those waters. The ice is pretty much gone, so that heat diffuses, fluxes to the atmosphere, and you got your little hot spot right there. This is the effect of the North Atlantic. And keep in mind, like right now, the Mediterranean is 6 degrees C warmer than average. And that heat is just going to rip raw eventually right into here. Granted, it will be less than 6C normal by the time it travels to higher latitude, but still, it will be significant heat energy being brought in. So we're seeing, I will argue, we are seeing the effects of the North Atlantic intermediate water with the heat flux, because the Barents basically has no more ice. That heat is fluxing right out. Because next is the Laptev and next is the Kara, then the Laptev and the East Siberian. So I would make that argument, but we can see very clearly the local amplification. So if you go down to 60 degrees north latitude, which is about here, okay, this is Alaska. So this is about Anchorage, which is pretty close to 60. You can see that this area here is in the 1 to 2 realm. So they're arguing that by including that, it kind of masked the actual warming. In other words, the signal was decreased, was not as great a signal. So by excluding these other latitudes, they say we're truly seeing what's going on in the Arctic. I understand the logic, and I'm not quibbling with that. I'm just simply saying pick a fixed latitude, because the Arctic Circle latitude does change. It moves south and moves north. It's moving now because the Earth is wobbling now ever so slightly. And then when we get into just around where the Arctic Circle starts, we can see it's in the 2 to 3 realm. And then within the Arctic Circle, we get 3 to 4, 4 to 5, all the way up to 7. So when then you average that out, the saying it's 4 times faster. Okay, continuing on with the, and they say, of course, the observed Arctic amplification ratio depends on the area definition. The higher the Arctic latitude threshold, the stronger Arctic amplification it is, as a larger proportion of the area is ocean, where the Arctic amplification is strongest. And we just looked at that. And so here they have the latitudes 55, 60, and so on. And then in the years, and you can see that right from here, we have what, 3 to 4, and 4 to 5, 5 to 6, 6 to 7, and so on. But we can, you can basically see how when they set the latitude at higher location, we can definitely tell it's more pronounced how much warming has happened. Furthermore, I love this one. We found that climate models, when considered as a group, cannot reproduce the observed fourfold AA ratio of 79 to 2021. And we use the CMIP 5.6, MPIGE, and CAN ES Earth System Model 5 models. In other words, the models were masking how much warming is really taking place, underestimating how much warming was really taking place. Okay. Those models that show plausible Arctic warming trend typically have too much global warming. In contrast, those models that simulate global warming close to that observed generally have too weak Arctic warming. So they're identifying deficiencies in uh, in the models. So they have the different models here, and you can put the regression lines right through there to get an idea of the slope. Even when allowing a longer time window for the models than for observation, the difference between simulated and observed was found to be statistically significant, except for the CAN ESN. And let's see, do they have the entire? There we go. So, in other words, this is the warming ratio, the Arctic amplification ratio that they found, which in most of these here falls outside, but they're saying that this is within the 2 standard deviation. So, in other words, here, here, and here, the first 3, CMIP 5 and 6, and the MPIGE, this falls outside 2 standard deviations. That's how I'm interpreting what they're saying here. Whereas with this particular modeling, it falls within the 2 standard deviation. Yeah, I don't know why they reported a probability as a percentage. Probability is a decimal. So what they're saying is that if you look at the probability, I'm going to convert it to probability. So we have 0.006. Okay, that means it's a significant result. 0.028, significant result. If you are using the 95% level. And then we have, this is just 0. It's like complete miss. This is 0.054, which is greater than 0.05. So this would be a non-significant result. That's what they're saying here. So these 3 are significant results, meaning that, going back to how they originally described it, come on, close, is that these other models come up short. Their observations, based on what these models would predict, their observations is not in agreement with the models. The models underestimate. Arctic amplification has seasonal cycle with lower in the summer, higher in late autumn and winter. That makes perfect sense. CMIP6 models, which is supposed to be the latest updated one, systematically underestimate the observed Arctic amplification, especially during the melting season. A particularly interesting finding was anomalously high uh, Arctic amp in April. So let's take a look at what they're saying. There's the Arctic amp in April. So these are the red dots are the observations. Now what the CMIP is, these are all box and whisker plots here. So this horizontal, what is that? Pink? Whatever that color is, that's the median. That's the 50th percentile. So this this box represents the interquartile range. So this would be this lower horizontal line is the 25th percentile. This is the 75th percentile. So this represents 50% of your data. This is the low value. This is the high value. And as we can see in basically all of these, the observation, I mean, really, the only one is for March, where it's right at the 75th percentile. April is it's like beyond the high value. Same thing for May and June, and then this is the annual. So what they're basically showing is that the CMIP models is underestimating consistently. In most cases, their observation does not even, if it does fall on the box and whisker plot, it's on the towards the high end of the what the statistical analyses would reveal. And then for annual, again, it's outside the high value. So August is interesting because the observation is basically equal to the high value. So again, showing what they're basically is building the case that the previous models have been underestimated. That's what they're building the case in these in their presentation. So the final point here is this indicates that internal climate variability may have contributed considerably to the observed Arctic AMP ratio over 79 to 21. It is also possible climate models have biases, which makes them systematically underestimate the Arctic amplification. More research is needed. Translation, fund us. Okay, so let's go back to here then. Figure 3 demonstrates how the observed Arctic amplification has intensified in the course of time. And 43 refers to the 43-year period that their analysis covers. So the 43-year Arctic amplification derived from CMIP 5, 6, MPI, and CAN ESM. Realizations, the thin gray line, all for all 43-year periods ending in 2040. So they're extending it. The x-axis represents the ending year for the 43-year AA ratios. Thick black lines represents the ensemble mean. Calculates a mean of ratios, not ratio of means. Now I'm going to say, wait a sec. Mean of ratios, not ratio of means. Okay, what this is, you calculate the ratios first, then take its average. Not not simply just take the mean and then put it into a ratio. That makes sense? You calculate the ratios and then you average them. Whereas here, you just simply take the means, A to B kind of stuff, and look at that ratio. They're different. Okay, so they discuss figure 4. Okay, this is the one that I felt we needed to um, look at the original paper here. Figure 4 shows the Arctic amp as a function of the starting year used for calculating the trends. In general, the shorter the time period for which AA is calculated, the larger role internal variability plays, and therefore the ensemble spread of the model tends to explode towards the right side of the panels, i.e., towards shorter trend. Well, yeah, I mean, when you have longer time periods, there tends to be some smoothing of the data, and you can probably also identify outliers more readily versus a shorter time frame. Now, it's it's useful to do both. You may want to look at short-term trend and then compare it to long-term trend. So it's useful to do both. Okay, how does the planet warm compared to 1750? Okay, you can do that analysis. How does the planet compare what's going on now compared to 1951 to 1980 or 1981 to 2010? You can do those comparisons and then to the overall. So these comparisons do have their validity, depending on what it is, what kind of info you're trying to tease out. Say the long trends, on the other hand, are more representative of the forced amplification and therefore have less spread between the realizations. You observe that Arctic amp is outside the spread of the five on the wide range of the trend, and in CMIP6, the spread of the Arctic amp is clearly wider than in CMIP5, and thus the observed Arctic amp does not fall fully outside the CMIP6 at any starting year. I guess they're saying starting here, you just pick any of these here and look what's happening here. So I think, okay, so let's take a look. What else do they say here? For CMIP5, the observed AA is fully outside the ensemble spread at all 30 to 45-year trend, regardless of the southern boundary. That basically tells us CMIP5 is not a good model. I'm just sum it up for you right there. Okay, so let's look at the full size image of this model here. The end year of all linear trends is fixed to 2021. Thus, for example, 1950 on the x-axis, that'd be here on all four panels, corresponds to Arctic amplification calculated for 50 to 2021. Okay, now I understand what they're getting at. Thick black lines represent the ensemble mean Arctic amp. Okay, so this black line is the average of all these thin little squiggly gray lines here. Okay. And it's calculated as a mean of ratios. Arctic amp ratio shorter than 10 years are not shown. The dashed vertical line represents the 43-year Arctic amp as calculated for 79 to 2021. That would be this in all four panels. So that would correspond to 1979. Okay. And so that's what they're basing it on. All right, now I understand what they're getting at here. So, all right. We can see, if you look at this red line here, it's out totally outside all of their what the CMIP5 indicates. Almost outside here, but it is contained within the CMIP6. Outside for a good chunk of the MPIGE modeling, And you can now see how the CANESM5 overall is the best model of these. First of all, you can see that the slope up until this point here, the slope here closely tracked. You can see that their observation falls within what the models would indicate. If you look at these lines here, these black lines, it's mean. All right, these are the means here. You can see how the ratio is much higher. So I can understand now why they're saying that this model performs the best. I can see that now. So let's get into the discussion. We present evidence that during 79 to 21, the Arctic has been warming 4 times as fast as the entire globe. Thus, we caution that referring to Arctic warming as being twice is a clear underestimation. And if you recall some of my videos from like last year or so, I was like saying, "Hey, it's 3 to 4 times faster." So I was kind of clued into what the trends were, if I may say so myself. There are 2 main reasons why our calculation of AA is greater than earlier estimates. Early estimates may be outdated due to continual warming in the Arctic, figures 1A and 3. The period of interest in the area Arctic can be defined in multiple ways. We use the satellite era when remote sense observations from the Arctic are available, and we define the Arctic using the Arctic Circle as the southern boundary. And I discussed with you my concerns with that. And they basically go on to say that we have improved methodology here. And they go on to say that there's some issues with observations, that there's, low number of observations, which can, of course, present issues when, trying to state with any confidence any trends. And they go on to say, for example, Simmons et al. Discusses the peculiar cooling or the lack of warming trend in ERA5 in the north area of Greenland and linked this with questionably low values of the sea ice concentration. This inconsistency in the temperature trend is also visible in our study. On the other hand, in figure S2, that's a supplemental figure that was not included in the main paper. On the other hand, it has been evaluated that out of 5 different reanalysis data sets, ERA5 performs best over the open Arctic Ocean. ERA5 was found to generally describe well the temporal and spatial characteristics of near surface temperature in the Arctic in 79 and 2014. Nevertheless, when averaging temperature trends, the inconsistencies seem to cancel out. Excuse me, I'm losing my voice here. As a result, the regional averages are surprisingly well aligned, and they're referred to as supplemental figure 4A. One potential factor increasing the observed AA is the hiatus phase in global warming that occurred between 98 and 2012. Well, a long time ago, I did a video basically saying that this hiatus um, did not happen. There was no hiatus in global warming. Statistical analyses debunked that. That's something the climate deniers like throwing out. Well, there was no warming here. Well, that's been debunked. So let's put that aside. Okay, so they talk about problems with the models and errors and so forth. They get into the what they did for the methods. So I will leave the URL in the comments section for those who want to further look at this in greater detail. This is what I wanted to discuss with you. Defining the Arctic amplification. It's science. We use math. We follow the recommendation of Smith et al. And define Arctic amplification as the ratio of Arctic warming to the global mean warming. Arctic amplification ratio. So in other words, the rate of change in temperature with respect to the rate of change in time for the Arctic, right? So this is the derivative, the rate of change in the temperature with respect to time for the Arctic, divided through by the rate of change in temperature with respect to time for the global mean warming. That is defining. And that's the slope. Remember that earlier figure I showed you where the slope was like about 4 times higher? That's where it comes from. It comes from this formulation right there. And they say dt dta, dt dtg are the slopes of linear trends of near surface temperature, 2 meters, calculated using a least squares fitting for the annual and monthly mean value. That's, of course, is a regression technique. The trends were calculated for different time periods, but 43-year AA ratios, referred to as AA43, were chosen to be of primary interest because 43-year covers the majority of the recent warming period, and three analysis products, ERA5, shown to be more reliable. And got satellite data. So, very interesting study. It's a starting point. Overall, the data does show, and that's kind of what the crux of it right here, and here, this figure, probably the important one of the paper. But there's your 4-to-1 ratio right there. So, we see it's much warmer, much higher slope than the global average. So as I said, it's a starting point. I think they are correct in challenging previous models' work, showing how there's underestimation going on. So that is so in that sense, this paper is important and is an important contributor. They are also quantifying it mathematically. There will be plenty to, I mean, I offer some of my critiques here, and there'll be plenty critiques for others to indicate. But, that's science. You have to start somewhere. And this is a starting point. Let's see what I hope they follow up on this. It sounds like they will, and continue examining this and maybe refining and fine tuning their analyses and the modeling to get even improved estimates. But yeah, Arctic amplification, it's not just something. Oh, that's very curious for the Arctic, but as I've said before, what happens in the Arctic does not stay in the Arctic. That Arctic amplification is spilling over the rest of the planet. And we're seeing it. Heat waves, droughts, right? Fires. I mean, warmer air can hold more moisture and does what? Sucks the moisture out of the ground. Oh, geez, look. Now the Arctic is burning down. Look at the fires in Siberia, Alaska, Scandinavia in recent years. So, the Arctic warming 4 times faster, or nearly 4 times faster than the rest of the globe. And it'll probably continue and increase. As I said, I will leave the URL in the comments section below. Thank you for your time.